Today's lesson is on gas stoichiometry. We'll start by looking at an example. So turn to page 424, example 1220 at the bottom of the page, read along. What volume of oxygen gas at STB can be produced by heating 112 grams of potassium chlorate? So we have to start off with a balanced equation for the reaction. So let's just, let me work this out for you here. You can add this to the bottom of the page in your notes if you want, or just follow along in the book. We need a balance equation for the reaction, and that's given right above the example problem. So when chlorates decompose, they decompose into chlorides and oxygen. And so let's go ahead and balance this equation. Potassium chlorate is a solid. And this is just a stoichiometry problem. So we're given the amount of potassium chlorate. We have 112 grams of this, and we're trying to find how much of the gas is produced at STP. And so we can just take the 112 grams and using the molar mass, convert that to moles. So molar mass of potassium chlorate is about 123. Now, there's actually a couple different ways we can do this. We can use the mass of potassium chlorate to find moles of oxygen. So if we just stopped here, let's say. And then we could take that moles of oxygen and plug it into the ideal gas law along with the temperature and the pressure. So this is especially important if the gas that is being produced is not produced at STP, then we'd have to use the ideal gas law. But in this event, the gas that is produced is at STP, and so we can use the standard molar volume of a gas. 1 mole of any gas at STP occupies a space of 22.4 liters, and we can get our answer that way. So you could also use the ideal gas law, even though it's standard temperature and pressure, but this is a easier way. If you plugged into the ideal gas law, standard temperature, standard pressure are 1 mole, guess what number you would get? You would get 22.4 liters. So that's how you do that one. Next up, we have Gay-Lussac's law of combining volumes, which states at constant temperature and pressure, the volumes of reacting gases can be expressed as a ratio of simple whole numbers. Let me reword this. Let's take a look at the example that's actually at the top of page 426. So how can we interpret this equation? One way is through relative number of particles. 2 molecules of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia, which is really not useful. We're never dealing with such small quantities. Another way we can interpret this equation is 2 moles of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. We can take it a step further. If what you are comparing are both gases, so if you're doing a stoichiometry problem and what you're comparing are both gases, then the coefficients in the chemical equation represent relative volumes. So for example, 2 liters of nitrogen reacts with 3 liters of hydrogen to produce 2 liters of ammonia. And it doesn't have to be liters, so your book uses just volumes, relative volumes. But oftentimes we're dealing with gases, the amounts of gases in liters. So just wanted to take that interpretation of the coefficients in a chemical equation. They represent relative volumes if what you're comparing are gases. Let's take a look at an example on page 441. A little hint on this one, we are given the amounts of both reactants. So this is a limiting reactant problem, so be sure to first find the limiting reactants and then use that to answer the question. Go ahead and pause the video now and work on that. So here's a setup. I decided to take the volume ratio and compare it to the needed ratio. So kind of like what we do with mole ratios, except we can just use volumes. You don't need to use ideal gas law and plug in some random temperature and pressure and find moles. Again, knowing that relative volumes are the same as relative moles for gases. So it looks like we have an available ratio, 1.6 liters of oxygen for every 1 liter of ammonia. If we look at the balance equation, we have 5-to-4 ratio, so make sure to do the ratio in the same order. We have 1.25 liters of oxygen needed for every 1 liter of ammonia, so that means we have more oxygen than we need. Therefore, ammonia is the limiting reactant. And we'll take that and use that to answer the question. We can use that to find liters of nitric oxide, NO, which is a 1-to-1 ratio, so 12.50 liters. And then also use it to find the volume of steam, which in this case is 18.75 liters. 425, here's what I was talking about earlier. Read along, please. It says a 1.80 gram mixture of potassium chlorate and potassium chloride was heated until all of the potassium chlorate had decomposed. After being dried, the liberated oxygen, meaning the oxygen that was produced, occupied 405 milliliters at 25 degrees Celsius when the barometric pressure was 745 torr. How many moles of oxygen were produced, and what was the percentage of the mixture that was potassium chlorate? So we start off with grams of potassium chlorate, use that ultimately to find moles of oxygen, just using the chemical equation. And then to find volume of oxygen, if we're asked to find that, we could use the ideal gas law. Here, the book is showing using the ideal gas law to find moles of oxygen. We don't have to do that. We can just use the stoichiometric ratio. Go from grams of potassium chlorate to moles of potassium chlorate, and then from moles to moles of oxygen. I'm not sure why they're using the ideal gas law here, but you can use the ideal gas law. And then we can use the moles of potassium chlorate to find, use moles of oxygen. So I'm looking at the letter B here, moles of oxygen to find grams of potassium chlorate that reacted. Take that divided by the grams of the mixture, and we'll get the percent of potassium chlorate. So it's a little different approach on a similar problem as 1220. All right, go to page 442. I'm going to work on exercise number 79. It is a green triangle, but I have confidence that you can do it. Go ahead and pause the video and work on that now, please. All right, so we have a two-step process for this chemical reaction where we have potassium peroxide reacting with water to produce potassium hydroxide and oxygen gas. And then that potassium hydroxide that is produced in the first step will react with carbon dioxide to make potassium bicarbonate. So for letter A, the volume of oxygen gas produced in the first step at STP, 0.295 liters or 295 milliliters. And then what volume would this occupy at body temperature, which is 37 Celsius and 1 atmosphere? So I used Boyle's law, or here you notice I use a ratio of temperature. Temperature is going up from 273 to 310, which is going to cause the volume to go up. And so I got 335 milliliters or 0.335 liters. For letter C, the potassium peroxide that is reacting will produce potassium hydroxide. So in letter C, you're asked to find the mass of potassium hydroxide that's produced. Just did a little grams to grams. We get 0.986 grams of potassium hydroxide, which is then used to react with carbon dioxide. And so they react in a 1-to-1 ratio. And we're trying to find, again, volume, this time of carbon dioxide that reacts at STP. So again, I use my standard molar volume of a gas as a conversion factor and got 0.394 or 0.394 liters or 394 milliliters of carbon dioxide that reacts. What volume of this carbon dioxide would react at body temperature? So again, used a ratio of temperatures just like before and got 447 milliliters or 0.447 liters. All right, that concludes this lesson. I'll have you do some practice with these types of calculations. Thanks for watching.